Hello everyone and welcome to a video about someone that we haven't previously talked about. The name is Pitch Lumen and they are asking the question, can gravity hold on? So I would suggest let's see what they have in stock for us.
Everybody, this is going to be a video talking about gravity and the atmosphere, and this is kind of an issue that's been brought up quite a bit in the cosmology discussion with the globe and the special center of creation Earth. And so I have a drawing here to kind of demonstrate a little bit about what the claim is, and
which I appreciate very much. All right, you know, usually the people we talk about just give the words and I need to decipher it, flatterd, and yeah, I appreciate that he actually made the effort of writing something down and illustrating it.
then what actually happens. And so here you have the Earth with the gas molecules here. You have a gradient, which is having very high density towards the surface. And
well, I mean, you say very high, but I mean, 100,000 pascals isn't really that much. But okay, sure. High density compared to no density, I guess.
And as you go further out, the gradient gets less and less according to the globe. Here you have plus level 10, we'll call it gravity. And as
level 10 gravity, I like it.
As you go further out, you get weaker and weaker gravity, or we'll call this minus sign level 1. And it is
I mean, yes, of course, gravity gets less as you go farther away. But as a matter of fact, you would get a gradient even if gravity was just a constant downward acceleration, like with no getting weaker if you go further away.
It's to a strong vacuum. So, gravity can hold the atmosphere to the Earth. That's the claim. Gravity can hold all of the densities of.
I like the expression gravity can hold all densities of the atmosphere to the Earth's surface. All densities is an interesting way of thinking about it. I would rather say that at sea level, the density that we have of air is due to the magnitude of Earth's gravitational pull on the composition of gases that make up the air there.
Atmosphere to the surface, including this layer, so including the most dense layer. And that is what would be happening here. So using the Earth's gravity at plus strength, you're holding this density to the Earth.
I am afraid I already spotted your mistake. You're supposing that the only reason why we have a gradient is because gravity becomes weaker, or gravity changes, but that is not the case. It's because gases are compressible, and thus you get well, air is compressible at the very least, thus you get a gradient. I calculated that in a previous video. I encourage you to watch it. I will link it in the description.
As well as all of these other densities with weaker gravity. And so this is kind of a cleaner drawing to depict the surface of the Earth with the plus level gravity, holding the most dense layer of gravity to the Earth using plus again. And we'll just say this is...
Why not numbers? Why plus?
Gravity within 100 feet, using atmosphere within 100 feet. So G within 100 feet holds the densest layer of atmosphere.
I mean, you I guess could think of it like that, but it's simplified and it ignores the rest of the atmosphere also pushing down on that one layer, you know, and that's important. It's really important.
Now, if you set up a experiment where you have 1 equal to, or density level 1, or 1 density level of marked by 1, you have the same density marked by 2. It's
I think he wants to say a packet of the same gas that is the same density as his packet number 1.
The same density, and you keep G equal to G.
Note that he uses big G here, and big G is the gravitational constant that really doesn't have anything to do with how much something is being accelerated, which is little g. So a bit irritating to use big G, because obviously big G wouldn't change.
Which is what you would be doing.
Because it's a fundamental constant of nature. It just gives you by how much kind of the factor is in between an attraction in terms of newtons and the magnitude of the masses and the distance.
You'd be using that plus gravity, and you would be holding the same level of atmosphere, or same density of atmosphere. So you have the same density should be held with the same gravity. And so then you would run this in a lab. You would have a weaker vacuum because we cannot make a vacuum as strong as outer space. And you would put a box of density 2 of atmosphere, which is equal to the most dense layer within 100 feet of the surface. And actually, because we would be doing this experiment on Earth, this box would be subject to plus level gravity, level 10.
I I mean, like, credit where credit is due. At least he's explaining it properly with illustrations, right? So that's you know. But the plus level gravity still is a bit funny.
Gravity, because you're at the surface of the Earth doing this experiment. So you would actually get the Earth to provide the constant of gravity. Therefore, G.
But you ignore that there is no atmosphere pushing down on that gas right now. So because it doesn't have the push of the gas from above, if you want to see it like that, of course the gas would expand a bit. And depending on how the scale of your experiment is, which you haven't specified, which makes it incredibly difficult to make any predictions, you would get strong layering or weak layering depending on how the scale is. Of course, if the scale is like, if that's a box that could fit in a room, well, then you won't get much layering at all.
G equals G. So the conclusion is that, or the possible options is that you can have gas 1 is claimed to be held at G, therefore gas 2 should be held at G. That is the...
No, that is not a valid conclusion. It ignores why gas is compressed, or as you would say, at a certain density at sea level, and it kind of also ignores how gases work in general.
Conclusion that the globe makes. Now you go down here and you get 2 results. You can either have the gas stay held in the box, like example 1, which would support the globe, because that is what is happening, is you have Earth's gravity holding that density of air down, strapped down, or you would get a dispersion of gas molecules showing that the strongest level of gravity...
Again, you're being vague here, maybe on purpose, maybe because you genuinely don't know, but yes, the gas is going to dissipate, but not equally, and that's the point behind it. There is, if you do that with a sizable amount of gas, not like a handful of molecules, and if you do that with a reasonable size, a room, or like a bath in the room, then you can reliably measure gradient also within that experiment. So neither of these 2 results would happen, because neither of them really show an understanding of physics. What would actually happen is, depending on how much there is, let's say that it's like a standard room, maybe a bit bigger than a room, like a warehouse room or something, and you release a reasonable amount of gas, what would happen is that at the bottom there would be a bit more gas than at the top, and if you have a barometer that is suitable for measuring a difference in pressure that you would expect at however high this room is, then you can measure it, and then you can come to the conclusion that indeed there is a pressure gradient. Now, I find it interesting that you say on the globe model there's a pressure gradient. I believe you said that earlier, making me believe that you don't believe that there's a pressure gradient. Then what I would ask you, if you go up a hill, why is there less pressure there? Or in the extreme case, on top of a mountain or in an airplane, why is there less pressure there? But you know,
gravity is not able to contain gas molecules, and that they would disperse into the vacuum, aka our atmosphere would blow off into outer space. So the result actually, the result 1 would support the globe, result 2 would refute the globe, and we get result 2.
No, result 1 would kill everything we know about gases. And result 2, depending on the scale of things, in smaller scales, can very well agree with the globe.
When we do this. So this is a refutation of the globe, showing that this can't actually happen. You can't have very dense atmosphere with plus level gravity, keeping it constant, keeping very dense atmosphere plus level gravity, very dense atmosphere plus level gravity. It does not hold. So
that's wrong.
refutes the globe.
It doesn't. It kind of shows that you don't really understand all too much about physics, especially in regards to gases.
One of many things, but this is just a claim that violates science, violates natural physical law, natural observations that we make, and experiments that we're
like the kind of observations that we've been doing for the last couple of thousand years that have shown us that the Earth's a globe. for example, just
able to carry out. So this actually refutes the globe and therefore is more valid.
Do you think that within the last couple of thousand years, or like I give you 100, right? Since science has started kind of properly, no one would have noticed. No? Okay, cool.
To the special center of Earth creation, emphasis on special, because we are very special. All of us are. We're all uniquely made. Our Creator loves us all. Yah loves us so much more than we could know. So much so that He sent His only.
Also, two things that I would like to mention, because the apparently very religious flat earther here is going on a ramble about creation and all that nonsense. This cursor here isn't mine. This is mine, clearly. I don't know where this one's coming from. And it's been there pretty much throughout the whole video, and I don't know why. I find that interesting.
Begotten Son, Jesus, to show us how.
Okay, yeah, we can stop it right there, and I can go over to my explanation OneNote. So here we are in the explanation OneNote that all of my channel viewers are so accustomed to. First of all, I would like to state that this is like iteration number 1073 or something of explaining gravity and atmosphere to people. Okay, and this is obviously not to scale, clearly. First of all, the acceleration due to gravity is the gravitational constant times the mass of the body that you're looking at, in this case we're looking at Earth, divided by the distance you have to its center of mass squared. So at 0 meters you get an gravitational acceleration of about 9.8. We know that. Depends on where you are at Earth a bit because of varying densities of the ground and stuff like that, but in general you can say 9.1 is sufficient for almost all explanations. Now when you go 100 kilometers up, you only have a decrease of about 3% to 9.5 meters per second squared. So I mean, there's really not that much difference, but there's a very, very, very big difference in density of the air at that level. So I would propose that it is extremely unlikely, when thinking about it, that the change in density of the air comes just from a change in gravitational attraction, right? So, or acceleration, really. So, yeah, that is a conclusion that I would draw here and that I think is reasonable to make. And as I have calculated previously, again, I will link the video in the description below. This can be explained very well with just gas laws and even constant gravity. You don't even need changing gravity for that. You can explain it with constant gravity. Take the natural gas law, the ideal gas law, if you will, not natural gas, ideal gas, because there's a slight difference. I'm sorry. You take the ideal gas law, you rearrange it so that it includes density, because we will need it later. You take the hydrostatic pressure formula, which is given as that, where G here is a constant, just 9.8. That's completely enough. You divide the two, then you integrate, you do the separation of variables, you integrate, you solve this integral right here, which is a very easy integral. This is about the easiest that an integral can be, really. Then you introduce a constant that is known as the scale height. I talk about it a lot because it is so nice, because it can predict where the atmosphere has dropped by a factor of 1 over the Euler's number E. And the neat thing is that this follows from gravity being a thing, and you can actually go up that high and you can measure it. And would you look at that, within reasonable deviances due to weather and due to air behaving not quite as an ideal gas, but as a natural gas, or like a real gas, as it is sometimes called. But in general, at about that height, I believe it's 3 point something kilometers, I keep forgetting, you actually measure a drop in air density or like air pressure to exactly that degree. So a gradient can actually just be explained by gas laws and gravity. You don't need anything else. And about your lab recreation, we don't have enough information about it. What's the dimensions? Are we talking meters? Are we talking kilometers? Are we talking, how much gas are we talking? In general, and that's the best prediction I could come up with, the gas will spread out and form a gradient, but depending on the scale, it will be very, very obvious, such as on Earth, or barely measurable if it's only a few meters or even less than that. Small-scale experiments like don't disagree with gravity. Like I can already hear Flatzoid pointing out his demonstration with the guy holding two flasks that aren't even half a meter to combined. But at that scale, also they are not making an effort to measure that, right? So at that scale, you just can't measure that little pressure change reliably with tools that we have at hand. Of course, you can measure them with specialized equipment, right? But not with something that you and I could do. I mean, I could borrow it from our lab at the university, but like I at home probably couldn't, or like only with figuring out a lot about it. But and you also certainly can't see it, right? Flat earthers sometimes expected you could see a change in gas pressure or something like that, which is completely ridiculous. Yeah, so in conclusion, you don't appear to have the most firm grasp on physics. I would encourage you to read up on a couple of gas laws and maybe do some introductory courses on classical mechanics or like videos or something like that. But in any case, that was a rather weak attempt and rather Flatzoidian. However, Flatzoid wouldn't provide that nice of a depiction, so kudos to you there. And with that, I believe that we have already been talking about it long enough. I hope you enjoyed this video. If you did enjoy it, please consider leaving a like. If you enjoyed it a lot, maybe considering subscribing, and I will see you in the next video. Until then, have a nice time. Goodbye!